Okay, going back to our pyramid problem yesterday. I forgot to save it, so I'm trying to catch up here. Let's see here. 10590.63. Okay, what we're trying to do is we're trying to calculate the velocity at the very bottom, the kinetic energy at the very bottom. Some things that we did. What we're going to do is we're going to do what we did initially a couple chapters ago, and then compare that to what we're doing right now with respect to kinetic and potential energy. Because if I calculate my velocity at the very bottom, if I calculate the velocity at the very bottom, I'm going to have a kinetic energy. All the potential energy I had at the top should convert into kinetic energy at the bottom. But what we have to worry about is friction. Friction is going to dissipate. We're going to lose some energy because of thermal energy. Okay, so we have to worry about the idea of friction here. So what we're going to do is we're going to work at old school and just an inclined plane, and then compare it to the kinetic energy and potential energy, what occurs. We have mu is equal to 0.45. Our force of friction is mu times our force perpendicular, our force normal. Did we calculate this yesterday? All right, 3723.44. We good with that? What did we calculate? What did we get? What?
I got 3,700.8.
3,700.8. 0.24, so we're off by a dime or a couple dimes there. Okay, and that's just, I actually just took the 1370 times 9.81 times the sine of 70 times 0.45. So I kept all my decimal places and I just kept on hitting enter. So we should be somewhere around the 3723.44, but once again, you should be off by, you might be off a few pennies. Don't worry about it, off by a few pennies. Okay. Now, that is our force of friction. We have our force parallel. We have our force parallel, which is sliding it down the plane. We have a force friction sliding up the plane. So we have force of friction coming at or going resisting our motion. So our net force is equal to our force of gravity, or force parallel, plus our force of friction, which is going to be negative. So we have the 10,590.63 minus 3723.44. Those are all in newtons. So our net force should be 6867.19. Once again, if you're out by a few pennies, don't worry about that. Newtons. That is your net force. And what we have talked about is our net force from Newton's second law is equal to mass times acceleration. What this will enable us to do is find the acceleration, because we have a net force of 6867.19 is equal to our mass, which is, let's see here, 1370 kilograms times our acceleration. So dividing both sides, we can find our acceleration. Nate, what do you get for the acceleration? 5.01 meters per second squared. So we are accelerating, this rock is accelerating, sliding down. So we have acceleration. We have initially velocity is equal to 0. Our goal is to find the final velocity down here. Well, I know acceleration, I know initial velocity, I don't know time, and I don't know a displacement. But I do have a triangle here. The height of this pyramid is 147 meters. I have this angle is 52 degrees. I can use my good old buddy Pythagoras and my trig ratios to find that displacement. Which trig ratio would relate this angle to these two sides? Lucas? Which trig ratio would relate this angle to these two sides? The sine, that's correct. So we have the sine of 52 degrees is equal to 147 over d. So we can multiply both sides by d and divide by the sine of 52. So we can find a displacement. How far does the rock slide down the inclined plane? Brandon, how far?
186.55 meters.
So now we know a displacement. We know a displacement. We know an acceleration. We know an initial velocity. And we have an equation. V final squared is equal to V initial squared plus 2AD, which will allow us to find a final velocity of the block. Make sure you take the square root. Liam, what's your final velocity?
43.2 meters per second.
If that's our final velocity, we can then find our kinetic energy. 1/2 mv squared. So we have 1/2 times our mass, which is the 1370, times 43.22 squared. Should get a really, really large number. Jordan, what do you come up with? And that's in joules. Now, once again, if you're off by a couple pennies here or a dollar or two, don't worry about it because it's just rounding. So at the top, we had this amount of energy, potential energy, 1,975,635 joules. At the bottom, we only have 1,279,000 and some more joules. Question is, what happened to the other joules of work? Well, that's where friction comes in. Let's think we have force of friction, which we calculated to be the 373,723 newtons. How much work was done by friction? Well, I have this force, and we have a distance of 186.55. So we have 3723.44 times this 187.55 or 86.55. So how much work did friction do? If you take that quantity and then add it to your kinetic energy at the bottom, you get somewhere close to the potential energy at the top. It won't be exact, but it'll be close. If I held all my decimal places, and did all my calculations holding my decimal places, it came down to the exact amount. How much work do we have there, Katie, with friction?
694,607.73.
And if we take this amount of joules and add it to this amount of work, or the kinetic energy at the bottom, we will be very close to the 1,975,000 and so on. In absence of friction, the energies would be the same. If this was an icy slope, then the kinetic energy at the bottom would be the same as the potential energy at the top. But since we have friction, that energy, as we talked about the other day, energy will not be conserved when you have non-mechanical energy. But when you have no friction at all, that's the main deterrent to mechanical energy. If when you have friction in there, you have to take care of the friction idea also. The energies will not be conserved. But if this was on ice going down and we have a ski slope, then the energies at the bottom would be the same as the energies at the top. But since we have friction, we have to take that into account, this idea of friction. Okay, what else I gave you yesterday? I gave you some homework. I gave you a review sheet. We're going to have a quiz tomorrow on just the energies. Okay, and this will lead into a chapter test. So the main emphasis will be for you to just work on the review sheet. Make sure that you know what's going on with respect to the review sheet. And we'll have a quiz tomorrow in regards to energies. Okay, the next thing then, after you get yourself prepared, you start working on the homework. That will be due sometime next week. Questions you have? All right, I think I've posted solutions to the review sheet. If not, I will post them. I also have them up here printed out. And the rest of the time is yours.